So we're going to be talking about electrolysis, and at the end we'll do electrolysis problem. An electrolysis reaction, an electrolytic cell is like a voltaic cell, except that we use energy from an outside source to drive a reaction that is not spontaneous. So in this case you see chloride ion, which is of course the more stable form of chlorine, and we are oxidizing it to chlorine. And then on the right-hand side of this compartment, we see sodium cation, which is the more stable form of sodium, and we are intentionally reducing that to form molten sodium. And so this reaction is extremely non-spontaneous, right? The opposite reaction, chlorine plus elemental sodium, would proceed gangbuster style to make sodium chloride, right, which is the more stable form. So in this case, we use an external battery that you see at the top in order to drive this reaction. We sort of intentionally push electrons into the sodium side and draw them out of the chloride side in order to sort of force this non-spontaneous reaction to move forward. So we use a battery as an external energy source. Now, in an electrolysis problem, we're really talking about electroplating. We're gonna add electricity in the form of a current. So current is in the form of amperes or amps. Amps are really coulombs that are supplied. It's sort of the rate of coulomb flow through a wire. So it's coulombs, which is a unit of charge, over time. So it's coulombs per second is 1 amp. 1 coulomb per second is 1 ampere. So if you know the time that a current is applied and you know the current, then you know the charge that's basically applied. Faraday's constant, which is on the yellow sheet, 96,485 coulombs per mole of electrons. That's basically the number of coulombs in 1 mole of electrons. Once you know moles of electrons, you can convert to moles of whatever. You use the reaction. It's just a stoichiometric relationship between number of electrons and the moles of whatever metal we're forming. So we're going to do an example that hopefully will make sense. So what we're talking about is electroplating. So on the left-hand side, we have inserted a metal into a solution that contained, on the left-hand side, I don't know what that is on the left-hand side. That might be silver. The right-hand side is definitely copper. So we've intentionally electroplated copper. You can see the blue solution is copper ion. And by inserting an electrode into that and supplying electricity, we can attach copper ion to the outside of that electrode. So we're going to do this calculation as an example. A solution of gold ion is electrolyzed using a current of 10.5 amperes. What mass of gold, so how many grams, will be formed after 5 days of giving it this current? So we're going to use this flow chart at the bottom to do this problem. Okay, so we're going to do this electrolysis problem. Just to conceptualize and make sure everybody understands, we have a gold solution. We're going to stick a metal electrode in that and supply electrons from an external energy source like a battery or the wall, you know, electricity from the wall. And we're hoping to convert the gold cation to solid gold. And of course, the longer we leave the electricity on, the more gold we make. This is the balanced half reaction. We need 3 electrons added to gold 3 ion to make an atom of gold solid. And so the stoichiometry is 1 to 3. That's really all we need for this problem. You don't need the reduction potential or anything like that. So we're going to start with the numbers that are given in the problem. We know that there are 10.5 amps that are given. So 10.5 amps is the same as 10.5 coulombs per second. We're going to convert the time, 5 days, into seconds because the amperes are in coulombs per second. So 5 days times 24 hours in a day times 60 minutes in an hour times 60 seconds in a minute gives us 432,000 seconds. So we're going to multiply that by the amperes. That gives us 4.536 times 10 to the 6 coulombs. So that's a lot of coulombs because the electricity was turned on for 5 whole days. So now we're going to take those coulombs, and remember Faraday's constant, which is on your yellow sheet, tells you not only how many, you use that not only when you're converting potential into delta G, or delta G into electrical potential, but we also use that number because it is the number of coulombs in 1 mole of electrons. And so the number on the sheet is actually 96,500. I use 96,485 just because that's the number in my brain. Of course, you will use the number on the sheet because that you don't have to memorize it that way, you just know it. I use it enough that I remember it. So coulombs cancel, and that tells us how many moles of electrons are supplied because we turn the electricity on at 10.5 amps for 5 days. So that means that we have supplied the reaction with 47 moles of electrons. Now we use the stoichiometry in the equation, which is here, 1 to 3, which means we're going to divide by 3 moles of electrons per 1 mole of gold, because we need 3 moles of electrons for every 1 mole of gold ion, or gold atom, or both. And then we multiply by the atomic mass of gold, and that gives us 3.09 times 10 to the third grams, or about 3 kilograms. Significant figures, you're given 10.5 amps, which has 3 sig figs. What was the time? Was that 5.0 days? Shoot. My sig figs might be wrong there. Because however many days you were given. If that was 5.0, then this should really be 3.1 kilograms. But I erased it, sorry. It is definitely 5.0 days. I just checked the problem. And so this should really be 3.1 times 10 to the 3 grams. It should really be 2 sig figs here.